A red ball A is thrown vertically upwards with a speed of 10 meters per second from a height of 240 meters. Simultaneously, from the same height, a blue ball is thrown vertically upwards with a speed of 40 meters per second. And we can see that the red ball lands first, while the blue ball lands a little later. We have to plot the graph of the relative displacement of ball B with respect to ball A right from the time they are thrown until the time they both strike the ground. Let's take the ground as the reference, and we use the second equation of motion. Now for the red ball A, the initial displacement is 240 meters. The initial velocity is 10 meters per second, and the acceleration is minus 10 meters per second squared, since the acceleration due to gravity acts downwards. For the blue ball, the only change is the initial velocity, which in this case is 40 meters per second. In these equations, we can easily obtain the time taken by the balls to strike the ground. In this equation, if we substitute YA, the final displacement, as 0, then we will obtain the time as 8 seconds. This means that it takes 8 seconds for A to fall to the ground. If we substitute YB, the final displacement, as 0 in this equation, then we obtain the time as 12 seconds. This means that it takes 12 seconds for ball B to fall to the ground. So ball B takes 4 seconds more than A to fall to the ground. Now we need to find the relative displacement of ball B with respect to ball A. We have to divide the problem into two parts. One, when both A and B are in motion, like in this animation. This is in the first 8 seconds. And the second part, when B is in motion and A is already at rest after striking the ground. And this scenario will be after 8 seconds, lasting for a period of 4 seconds. Let's take the first case, where both A and B are in motion, and in this scenario, the relative displacement of B with respect to A, y B with respect to A, is the displacement of B with respect to the ground minus the displacement of A with respect to the ground. And this is the scene at the end of the 8th second, where ball A has reached the ground and ball B is still in motion. In the previous step, we had computed both these, YA and YB. Subtracting YB from YA, we obtain the relative displacement YB with respect to A as 30t. Now this is for the first part where both are in motion, that is, the first 8 seconds. Here you can see that since both the accelerations for A and B are identical, their relative acceleration is 0, and therefore their relative velocity will be a uniform velocity, and that would imply that the relative displacement would be a linear function of time. So you can see in this case, the relative displacement is 30t. And we have to plot this function over a period of 8 seconds, that is, until A reaches the ground. So let's proceed to plot the graph. Now we plot the graph for the relative displacement of B with respect to A for the first part, that is, until A strikes the ground, which takes 8 seconds. So we plot the relative displacement yb with respect to A, or 30t, versus the time t on the x-axis. And over a period of 8 seconds, we can see that the relative displacement will be 30 times 8 or 240 meters. That would mean that at 8 seconds, when A reaches the ground, B is 240 meters above it, which indicates that B reaches back to its launch position, which is 240 meters above the ground. From the formula, you can see that this represents a straight line with a slope of 30. At this point, A has hit the ground. Now we have to handle the second part, that is, A is stationary on the ground and B will continue falling from this height of 240 meters towards the ground. This is the second part where A has already reached the ground and is stationary, while B falls to the ground. Again we set up the displacement equations. Here YA will be 0 since it remains on the ground at all times. And B is in free fall, so we will have a negative acceleration of minus g or minus 10. The relative displacement yb with respect to A, or yb minus ya, is in a quadratic form, and the coefficient of minus 5 before the t squared term tells us that the graph will not be a straight line, but some curve which will be a concave curve downwards. Let's plot this in the next step, and remember that this is only for the second part, where A is already on the ground and B is falling from a height of 240 meters. This part represents the second part, where B is in motion. B takes an additional 4 seconds to land, so we start the graph at t equals 8 and we obtain yb with respect to 8 for t equals 9, 10, 11 and 12 seconds and plot the displacements. And at time t equals 12, yb with respect to A will be 0, meaning that the displacement of B with respect to A is 0, and that indicates that B has also reached the ground. For the first part, the relative velocity is uniform, as there is no relative acceleration, so the relative displacement graph would be a straight line. For the second part, it has a negative relative acceleration, so you can see a downward concave for the displacement time graph, so this is not a straight line. And when there is a relative acceleration, like in this part, the relative velocity will no longer remain uniform, and therefore the relative displacement graph will be a curved line. When there is no relative acceleration between two bodies, the relative velocity between the bodies will be uniform, and therefore the relative displacement versus time graph would be a straight line. But when there is a relative acceleration between two bodies, the relative velocity will not be uniform. Therefore, the relative displacement versus time graph would no longer be a straight line.